Hi, next, I'm happy to introduce Professor Huazhe Xu. So Huazhe is an assistant professor at Tsinghua University and a co-founder of Galaxia AI, a startup advancing humanoid robots. He earned his PhD at UC Berkeley, followed by a postdoc at Stanford. His works have been recognized as the Best Assistant Paper Award at Coral 2023 and the Outstanding Student Paper Award finalist at RSS this year. I met Huazhe when I was an undergrad at Berkeley, and he's been a great mentor and friend ever since. I always enjoyed his perspectives on both research and industry. So please join me in welcoming Huazhe.
For the kind introduction. So today I will have a talk on robot OOD generalization does not exist. Since it's an OOD workshop, so I think it could be the best audience here. So OOD is a fancy word, right? Like when I see this word, I will think about true intelligence or AGI, etc. But when I work on like robotics, I find actually we cannot generalize to OOD tasks. Everything we can generalize or we claim we generalize is because we use some way to convert OOD things into ID, like in distribution tasks. This is the only way. This is the only way. That's my argument. Maybe it's too strong, but you can criticize. Great. So first, what is OOD? To me, I think OOD is not like this. There are a lot of blue dots. There are collected samples or existing data. And if you have one task lying here, I would say it's not OOD. For example, in a robot workspace, if you collected demonstrations all over the space, but you say, can you generalize to this location? I think, well, definitely you can generalize because it's in distribution, you can interpolate. Then what about this task? I have a lot of data here, existing data, but my task is right here. This is, sort of in between, like, it's OOD, it's ID, I don't know, because if it's move a little bit, inside is ID, but if it moves a little bit outside, it's OOD. For example, in this case, if I want to grab a mug, that's a robot arm, of course. Then I collected a lot of demos, and then I say, I didn't collect demo on this mug because it's too fat. And I say, on this super fat mug, can you grasp it? Can you pick it up? Then I would say we can generalize because it's so close to the distribution. But if it's another object, well, things will change. For example, here still, if I collected a lot of demonstrations on these mug picking up tasks, then can we ask a robot to make dumplings? I think the answer is a definite no, right? Because learning from those, in a low data regime to learn picking up cups or mugs, well, it can by no chance transfer to making dumplings. So in this case, our red dot is here. Right? It's super OOD, and we cannot generalize. So now I think we are kind of clear about what is OOD, or at least we have a categorization of OOD. Okay, so what's my solution to OOD? We first did a study about spatial generalization. So in this case, the green dots are demonstrations, like these green dots, and the blue area are generalizable areas. That means robots can succeed in these areas. And we find the more you collect, the more you generalize. There is no exceptions. Here, if you only collect one dots, then you only generalize around this. While you have slight generalization because there are some tolerance about picking up, right? Because you have the lens between the grippers. In this case, we say everything is ID. If I want the robot to generalize to this area, I have to collect all these data. But maybe we can do some other things. Maybe we can generate some data. maybe we can use some other models that is super smart, see a lot of data to help with that. Those are all solutions, but well, it's not OOD. We always convert them into ID things. So my argument here is OOD tasks exist, but we can only do ID generalization. What we can do is trying to make OOD tasks ID. Today I will share some of my thoughts. The first one is how can we add data? We can maybe blindly and diversely to add data to hope that the data would cover everything. Andrea might say no because it's too hard to cover everything. Or maybe you are a little bit smarter. You already know the target position, and you say, hey, maybe I should collect some data near my target distribution. That's also fine. Or you can use some more powerful tools like foundation models because they see a lot of data previously. Or you can use some sort of representation learning or leverage some symmetry or equivalence. So seemingly OOD tasks are actually ID. You just change your viewpoint to some extent. So first, add data. Still back to our blue dots. We are trying to tackle that OOD task. Then we just collect some more blue dots around the red dots. Then that's it. We can solve that. Or you can collect something new, or you can move some of your old data into the new distribution, right? That's one way. So we had a paper called Learning to Manipulate Anywhere, or nicknamed Manywhere. We want the robot to do zero-shot sim-to-real generalization, generalized to different domains like camera views, backgrounds, and unseen scenarios. So in this case, it's super OOD, right? It's sim-to-real plus the camera might move and the background might change and the whole scenario might change. So let's see the results first. So everything is only trained in one simulator, but when we test it in the real world, we will find it is very robust. We don't need to calibrate the camera. You just use a real sense and you plug it in and everything is done. You just run your policy and it successfully picks up the red cube. And next is my favorite part. You reset the scenario and then ask the robot to perform the actions again. But in the middle, he will shake the camera, and you will see even with very shaky camera, the robot can still generalize. It's very robust. Of course, we also use the same model. We didn't train another model, the same model in the kitchen sink. And we find it can generalize to an apple. And of course, it suffers a little bit and struggles to pick it up and failed a little bit and try to move and pick it up. So seems it's OOD generalization, right? Seems like we can generalize to super challenging scenarios. But let's look at the method. The method is very, very simple. It's just like two camera during training. And when you're in the simulator, there will be a fixed camera in the front. And there will be another camera trying to move all the way around the object or the target area. And you use some contrastive learning to learn a representation between these data. So it can generalize to different camera views. Yes, it can. But is it OOD generalization? Oh, task-wise it is, but method-wise it's not, because we have this kind of data augmentation inside our simulation. But more than that, we have a lot of other data augmentations to make it work. We have random translation, that's normal. We have random crop, that's normal. We have mix up, that's very important. We use places 365, the data set, combined with our real robot data set. There's a mix up technique to make it generalized to all kinds of background. We also use SRM, it's a spectral augmentation technique. You convert everything with Fourier transform into the spectral domain and then augment inside the spectral domain. So we add so much augmentation into this method so that it can generalize to all kinds of things. So this is our first method, try to add data. Maybe, some sort of blindly, because these things are just, blindly add more data, hope it covers everything. And these things are, because we know robot is very, fragile against different camera views. So we purposefully add this. Yeah. And the other thing, maybe some of you have already heard this in the conference, and the first author is there. So DemoGen, we also generate some data. So we can augment data, we can even generate data. So in DemoGen, we have action generation with temp, and then visual observation generation with 3D editing of the point clouds. I think, well, this video is still. Yeah, so it's very simple, right? You pick up this thing and put it here. And after you do the point cloud segmentation, you can move around it. And then you just do motion planning to pick up things at a different place. Then you can, generalize to all the workspace for every task with one single demo. But is it OOD generalization? I only have one demo, but I generalize to the whole tabletop? No, because we generalize, because we generate all kinds of demos all over the tabletop, so it can generalize. So it's still ID because we add data to make OOD locations, OOD space ID, right? So this is DemoGen, right? We also try by manual, and the interesting part about this is it can also generalize to different rotation, different orientation, right? That means you can, not only to translation, to orientation, and this is also showing it's robust to disturb, right? When we generated a lot of data, and then it can, mimic human interrupting the robot, and now everything is ID. So when we are doing this, maybe in the future, we should have an OOD task in our mind first. I think about how can we generate or how can we augment the data and to make it ID. So that's the first one. The second one is we can use some powerful tools such as foundation models. So in this case, we still want to solve that red dot, that OOD task. But in this case, the foundation models have seen a lot of data there. Maybe there, maybe there, maybe there. Okay, I copy paste too many times. Sorry about that. But anyways, our foundation model is like, everyone knows, trained with large scale internet data. So when we are trying to solve this with only some demos here, well, it's not so hard for them because they are trained with a lot of prior data that is near the red dots. So for example, this is a paper I stole from CBPR, I think, or ICCE. So the result is super cool. So when you click a dot on the beak of the duck, then they will find the correspondence on the beak of different kinds of birds, or even a bird in a or a duck in a picture, right? In a painting, right? So this kind of correspondence naturally exists in foundation models, and this is from diffusion. So when you train diffusion with large enough data, the correspondence naturally emerge. Although I would say, well, according to OOD definition, I would say these kind of things are sort of, moderately OOD to extremely OOD, right? So we leverage this kind of foundation model to handle those kind of OOD tasks. And we say, can we use this kind of, foundation model in robotics? And we say, when a human encounter novel categories of object, we learn by analogy, right? When we look at, the hammer, then we think maybe we know how to grasp a fork. Then maybe the hammer should be grasped the same way as how we do with a fork. Then we say, can we enable robot to do that? And the answer is very, very simple. We use diffusion features to do this kind of analogy. So here, this is a spoon. We can transfer that to a knife, and the interesting thing is this is a fork, and it can be transferred to a rose, because they share sort of similar geometric features, right? So with foundation models, we do have OOD generalization ability, but is it like truly OOD? Well, I doubt it, because stable diffusion see everything. So it's still ID, but we can solve OOD tasks with the ID generalization ability of foundation models. All right, so this paper is called Robo ABC. We have a screwdriver here. We use long sum to find the closest thing to it. Maybe it's a knife from a data set. And then we use the diffusion features to find correspondence between knife and the screwdriver. We call it affordance map. And then we use some sort of grasp net or any grasp to do the action. That's how we do generalization with stable diffusion. And the result is here. So all the numerical results are not so important, but if you look at these things, we will find one interesting conclusion is that using stable diffusion correspondence is much better than training affordance maps with a small data set. Right? There are a lot of data sets that is trying to do correspondence between objects. And with those specific data sets, we train our model and we find the correspondence is actually bad. At least worse than diffusion features automatic, training-free correspondence. So in this case, we all see the power of data. Diffusion is not trained to do this, but since it sees a lot of data, then the correspondence is naturally better than specifically designed data sets. Yeah, and here are some results. Maybe it's too small. We can generalize between a pen and a racket, or a bottle to a bowling ball, because they share some sort of correspondence because of diffusion find is corresponding. Yeah. And Robo ABC is improved recently called dense matter. Instead of having a 2D correspondence, 2D diffusion feature, we have a multi-view version of feature extracting, and then use fit up to have high resolution features, and then we reproject all the features to the 3D mesh, so that we can have correspondence between two different onions. Right? So there is no two onions are the same in the world, right? So if you already know how to cut one onion, you should know how to cut the other. But for robots, when the robots look at the other onion, it's OOD actually, because they have very different shape or maybe different color. But with foundation model features, we find they have very strong correspondence. And with those correspondence, we can actually generalize, right? So by using dense matter, we improve Robo ABC and to make it generalize better. And here, this is not robotics. We just trying to do color transfer. For example, this is a horse, this is a line, and then we can transfer the skin of the horse to the line here, because they have correspondence across categories. And for robotics, we can do human demonstration to human video demonstration to robot manipulation transfer. This is a human trying to peel a banana, and with the correspondence we learned, we can ask the robot to peel another banana, although they share they have different shapes. But foundation models tells us they are corresponding to each other. Let's see some video. Yeah, on the left is the human demonstration trying to peel the banana. And on the right, by only looking at this video, the robot can actually generalize to a new banana. Although they look similar, but it's new. Trust me, because it's already peeled. Right? So So then we say robot can actually generalize to OOD tasks with the help of foundation models, right? That's another claim. But the foundation models use a lot of data, so it's still ID. Okay, and lastly, we are trying to say some of the OOD tasks are actually ID tasks. For example, because I asked Gemini to help me to generate this because it's 3D image, and this PowerPoints I failed to generate by myself. So this is from Gemini. All the blue balls are here, and the red ball is here. So this is OOD, right? And if you look from a bird's eye view, then it's ID, right? Then it's ID. Actually, when you're looking at the from a different angle and you see the projection, then maybe actually it's in distribution. Just you didn't find the correct representation. You didn't find the correct viewpoint. For example, this is an old paper also from journal. It's called USeek, correspondence from equivalence. So in USeek, we are trying to manipulate a category of objects. For example, a category of airplanes, toy airplanes. And in this work, we first have some key point detection. We will find this kind of key points. And then, well, the teacher scale network doesn't really matter. And then we use a spring network to take in the point cloud and then have some feature. But the spring network is actually equivalent network. So if you rotate the airplane, if the airplane is slightly longer, slightly wider, then the features are very similar. They don't actually change. Although in RGB space, it's totally different, right? When you take a picture and rotate the airplane and take another picture, well, it's completely, maybe you might face some catastrophic things. But in the point cloud space with equivalent neural network, they're the same. Oh, there is no difference. So with USeek, we can first do key point detection. For example, this airplane, this green dot is corresponding to this green dot, is corresponding to this green dot. Well, they are rotated. And they have different, I think these airplanes are from different generations, but we still find the corresponding, key points on the nail, on the nose of the airplane and on the butt of the airplane. Yeah. So in this case, we also do some, real robot experiments, and my student Zhe Cheng is, trying to give one demonstration, maybe half of a demonstration, just showing one grasping pose. And then when the airplane is on a different location or on a different pose, then the robot arm can just deal with it. So any rotation, the robot can deal with it because it's equivalent. And there are more videos trying to show if you change the color, change the type of airplanes, it all works. I think I have some more demo. Let me jump a little bit. Yeah, in this case, we also tested on knives. And with half of a demo, the robot can actually grasp the knife and cut the tofu. With different color, with different orientation of knives, we can do the same. So it's sort of generalization. According our definition, everything is OOD, but well, actually it's ID. You just didn't see it, right? And this is a guitar toy placement like example. Yeah. So so later we have another paper trying to kind of follow this direction called Riemann. So in Riemann, we have another equivalent neural network and trying to also have the input as with a point cloud format And we have a saliency net trying to do automatic attention to the target location. So this kind of equivalent neural network is also robust to all kinds of orientations. I wouldn't go to details of this, but I will just show you the video. Yeah. So as you can see, these arrows are following the cup, and these arrows are predicted. Right. So with this kind of following technique, you can make your robot arm to follow different pose of the mug, and then it will zero shot generalize to OOD pose. And well, still again it's OOD, but to an equivalent neural network, it's actually ID. I also recommend you to read two other papers, not from my group. One is called Instant Policy. I think they also kind of leverage graph or topological similarity to trying to generalize zero shot. And the other one is called equivalent diffusion policy. I think that paper wins the best paper at Coral last year. And that's also another equivalent network. So all these kind of works trying to say if we have the correct neural network format, we can actually convert everything into the same problem. So lastly, some thoughts about generalization. So where there are data, there is generalization. So don't trust your intelligence, trust data. So collect more data, generate more data, and use more data. By generate, you can use foundation models to generate them. You can use some other hacky ways like DemoGen. You can use temp to generate data. That's fine. And collect data means you can hire, if you're rich, you can hire tail operators. If you are poor, and then you can use all kinds of data. For example, there are a lot of online human videos. Try to leverage those data to make your robot in a high data regime. Representation learning matters. You should find the correct representation so that you might convert the OOD task into ID. And lastly, this is kind of irrelevant to today's talk, but I really like factorized understanding and the evaluation of generalization. So like in the beginning, we are talking about what is OOD? What is OOD? Is changing color OOD? And is changing color to a changing shape OOD? Is changing camera view OOD? And how OOD it is? We don't have definition. So I think we need some factorized understanding and evaluation for generalization rather than just saying we can generalize, right? Because we cannot generalize to everything. Yeah. So and lastly, this is acknowledgement. These are all my amazing collaborators and the students, and most of work are done by them. I'm just talking. Yes, and thank you. Any questions?
So take questions. The next set of oral
does the second part of the talk subsume the first and third part? In the sense that if you have foundation models, you still need to do data augmentation and careful design of the architecture.
Yeah, I think to some extent, yes. Because foundation model, if you have foundation models of robots like VRA, if VRA really works, you can train VRA with human videos, then maybe no, you don't need the augmentation anymore. But if you are using like vision foundation models like diffusion or LLMs, I think you still need the augmentation things. Because for robot, there are some specific, generalization aspect you need to optimize. So you still need to maybe augment the random translation a little bit, or augment this mix up a little bit. Do you all agree that OOD doesn't exist? Oh, I wish correct it here. You might say Oh, they actually exist.
Maybe one question. Like I guess you're framing OOD as like zero shot out of distribution generalization, but maybe there's an argument to be made for like few shot quick adaptation, like autonomous adaptation, and maybe that would be possible. Like, yeah.
Yes. I think, sort of few shots adaptation is much, achievable than, zero shot OOD. I agree with that. And that's another thing I really liked. Like, can we leverage some online experience to do adaptation? I think there are two things. The first thing is you should have a strong prior. Right? Maybe you have a foundation model, or you have a hyper network, a working version of hyper network, to do fast adaptation. And the online experience learning algorithm should also work. You should have very high sample efficiency RL, or maybe contrastive learning. Because those two combined, maybe we can do fast adaptation. Yeah. There are no. Thank you, everyone.